Good morning, everyone. I'm Dr. A. Shanmugavani. So today I'm going to discuss about the Raman spectroscopy. Basically, the Raman spectroscopy is based on the inelastic scattering of monochromatic radiation by molecules. That is, when a beam of light is passed through the transparent material, a small amount of radiation energy is scattered. So this instant beam of light is nothing but a monochromatic radiation. That is, we can use a lasers, or this is having a very narrow frequency band, and the scattered energy will almost contain entirely of radiation of the incident frequency. But also, in addition to that, we can get some discrete frequencies below and above to that of the incident beam. So this is referred to as a Raman scattering. So it was discovered by C.V. Raman in 1928, known as the Raman effect. So when light interacts with the matter, most scattering is a Rayleigh scattering, while a very small fraction results in Raman scattering. Raman scattering occurs due to the interaction between the incident radiation and the molecular vibrations or rotations. So the quantum theory of Raman effect occurs due to the interaction between the photons and the molecules. So the incident photon of energy h nu interacts with the molecule and raises the molecule to a virtual energy state. If the molecule absorbs energy, the scattered photon has lower energy. So it produces a Stokes lines. If the molecule loses energy, the scattered photon has higher energy. It produces an anti-Stokes lines. Raman Rayleigh scattering occurs when no energy exchange takes place. So let the photon with energy h nu impinging on the molecule. After collision, the energy of the scattered photon is h nu, and it is given by the formula h nu plus incident photon energy gives the photon plus the energy of the scattered radiation. So here, Stokes lines are nearly 100 times more intense than the anti-Stokes lines. This is because only the molecules are in the vibrational excited state prior to irradiation may give rise to the anti-Stokes lines. So that kind of molecules is very less. So the intensity of the anti-Stokes lines is less, whereas the intensity of the Stokes lines is higher. So it is given by the formula number of molecules in the excited state by number of molecules in the ground state. That is equal to e power minus E by kT. So when come to the classical theory of the Raman effect, so mainly when a molecule is put in a static electric field, it suffers some distortion. That is, the positively charged nuclei is attracted towards the negative pole of the field, and the electrons to the positive side of the field. So this causes the separation. This separation of charge centers causes an induced electric dipole moment in the molecules, and so the molecule is said to be polarized. So it is given by the formula mu is equal to alpha into E. Mu is the polarizability of the molecule and E is the applied field. So the polarizability of the molecule in various direction is conventionally represented by drawing a polarizability ellipsoid. So for a first diatomic molecule H2 that is placed in an electric field. So here in end-on and sideways rotation, so the electrons forming the bond are more easily displaced by the field when the molecule is placed along the bond axis, whereas it is placed along across the bond axis. It is said to be the polarizability is said to be anisotropic. So it is given in the picture. So next, the pure rotational Raman spectra for linear molecules such as CO2, N2 and oxygen molecule. So it rotates about axis perpendicular to the molecular axis, and the rotational energy levels are given by Ej is equal to Bj into J plus 1. So we know that B is a rotational constant and J is a rotational quantum number. So in case of symmetric top molecules, examples are chloroform, that is CH3Cl and NH3 have two equal moments of inertia, one different moment of inertia. So here the rotation energy levels are given as E j comma k equal to B j into j plus 1 plus a minus b into k square. So As usual, B, A and B are the rotational constant for parallel and perpendicular axis. J is an angular quantum number. K is a projection along the symmetry axis. So the selection rules for the Raman spectroscopy is for linear molecules is given as delta J is equal to 0 and plus or minus 2. So the plus or positive 2 gives the Stokes lines, that is the photon with loses energy. So for delta J is equal to minus 2, it gives an anti-Stokes lines. So for symmetric top molecules, the parallel Raman bands are given as delta K is equal to 0. Here the angular quantum number J is equal to 0 or come up 0 plus or minus 2. And whereas if delta K is equal to plus or minus 1, we have delta J is equal to 0, comma plus or minus 1 and plus or minus 2. So the vibrational Raman spectroscopy for the non-linear triatomic molecule H2O is studied. So we know that vibrational Raman spectroscopy is a technique used to study the vibrational modes of molecules by measuring the inelastic scattering of light. So for a molecule is to be Raman active, its vibration must produce a change in polarizability. So here H2O is taken as an example. It is having a three fundamental vibration modes. So all the three five fundamental vibration modes are Raman active because they can cause a change in molecular polarizability. So the picture shows the three vibration modes of a H2O molecule along with its molecular polarizability ellipsoids. Symmetric stretching mode. During vibration, the size of the polarizability ellipsoid changes. So it produces significant change in polarizability, making the symmetric stretching mode, new one, is strongly Raman effective. So next to the bending mode, the shape of the polarizability ellipsoid changes during vibration. So the bending mode is also Raman effective. Similarly, asymmetric stretching mode, new 3. Here the direction and shape of the polarizability ellipsoid changes during vibration. So that is also Raman effective. Next comes the techniques of and the instrumentation part of the Raman spectrometer. So it is an analytical instrument used to measure the Raman scattering of light from molecules and provides the information about the vibrational and rotational energy levels. So typically we have incident for incident light, we are using a laser source that emits a monochromatic light to excite the samples, and the optical components such as lenses and mirrors are used to focus the laser on the sample and to collect the scattered light. So the elastically scattered Rayleigh light is much stronger than the inelastically scattered Raman light. Filters are used to block the Rayleigh component. The scatter light is then directed into a spectrometer, often containing a diffraction grating, which separates the Raman shifted light according to wavelength. Finally, a detector, usually a CCD or photomultiplier tube, is used to convert the light signals into electrical signal, then automatically processed by a software to plot the Raman spectrum, showing the vibrational modes of the sample. In modern Raman spectrometers, we are using the Fourier transform methods or modules uh, to make them highly sensitive and suitable for a wide range of molecular analysis. Thanks for listening. Thank you.